Welcome everyone to the AISTech 2021 Undergraduate Student Project Presentation Contest. My name is Courtney. I'm the Student Program Administrator here at AIST. I understand that things are a little bit different this year, but we definitely appreciate everyone's flexibility so we can still offer this contest. And before we get started, I just want to introduce our judges. So if you guys want to put your camera on, I will introduce you. Looks like the PowerPoint doesn't want to work. Oh, there we go. So first we have Kevin Board, who is from T-Mike Corporation Americas, and he will be serving as our moderator today. And we also have Kelly Dallas with us from Cleveland Cliffs, and of course, Amy Beard from Quaker Houghton as well. And so just a couple things to keep in mind as we're going throughout the contest today. The session will be recorded from start to finish, and it will be posted on AIST's YouTube page. So if you are not speaking or not presenting at the time, we ask that you just please mute your microphone and also turn off your camera. And then if it is your time slot to present and you are unable to share your screen at the time, I know some of you sent me your PowerPoints. So I will try to help you in that regard if you did get them sent to me. If not, then we will move your presentation to the end and you will get another try at the end of the schedule here. And so with that, I will pass things over to Kevin, our moderator.
Good morning, everyone, and thank you for joining. As Courtney said, this is a little bit different, but we'll get through it all. So I appreciate all the work that everyone's done. I'm looking forward to hearing your presentations. As Courtney said, I'm Kevin Board, and I'll be the moderator and one of your judges. And with me, of course, is Kelly Dallas from Cleveland Cliffs and Amy Beard from Quaker Houghton. And so we will be your judges. I'd like to remind everybody that we are competing for cash prizes, $500 for third place, $1,000 for second place, and $1,500 for first place. Also, I want to remind everyone, as Courtney said earlier, that this is being recorded and will be posted on the AIST YouTube channel. What I will do is I will introduce each one of you to start your presentation. You have 15 minutes for your presentation, and so please be mindful of that. And if you have time at the end of your presentations, there will be an opportunity for some Q&A. It's not necessary that you take all 15 minutes, but please be mindful of the 15 minutes. And so the other thing I would like to remind everybody is that there will be an awards presentation at the Tuesday night. There's a student reception, and for those of you who are unable to attend, there will be an email sent out announcing the contest winners. And so with that, if no one has any questions or anything before we get started, let's get started. And so what I'd like to do is first introduce Joseph Madrigal and Jose Martinez from Purdue University Northwest, and their topic is design of a steel annealing furnace rack.
Hi, can everybody see me okay? Can you hear me?
Yes, looks good.
Yes. Can everybody hear me?
Yes.
Yes.
Thank you. Okay. Hello, everyone. Thank you for being here. My name is Jose Abarca Martinez, and today with my partner, Joseph Madrigal, we will be presenting the design of a steel annealing furnace rack. This project has been provided by the Center for Innovation through Visualization and Simulation. also known as CIVIS, at Purdue University Northwest. Next slide, please. In this work, we are working with annealing furnace racks. As you can see, there's a picture on the right of the racks. These racks are designed and used to hold steel coils to undergo a spheroidization process. On the right top image, you can see a furnace model of the racks with 6 racks and 12 coils inside. A spheroidization annealing process reduces the steel strength and toughness, making it soft and machinable. A problem arises after the racks undergo several thermal cycles. These racks experience structural failures that require expensive repairs, such as stress cracking and warping. The bottom image shows the racks and coils in normal operation and the forklift that lifts them out of the furnace. Next slide, please. The objectives for this work was to modify the base rack design to remove or reduce some of the predictive failures. In order to do this, we performed second simulation of an alternate design as provided by industry using ANSYS finite element analysis, FEA. Additionally, we wanted to identify sources of failure and optimize the design in order to reduce damage. Additionally, we also wanted to reduce maintenance and replacement costs and ultimately provide industry a robust, cost-effective method and guide for improving the racks. It is important to cover the results of the current rack design. Through a successful simulation of the furnace operation, it was found that the temperature distribution resulted to be very minimal, as seen on the top right images. It's only of 2 degrees. This led us to conclude that the deformation as a result of the thermal expansion is very minimal, as you can see in the bottom right image. That deformation is in the X direction, and it's very minimal, not enough to cause failure. It was also found that the most effective material is AISI 304 stainless steel. And the main conclusion was that the rack fails from structural loading. As you can see in the bottom left image, you can see the stress distribution in the forklift channels. The approach for this project was an iterative approach. We start out by doing research, literature, analyzing the models in order to identify the areas of improvement and consider the constraints of the furnace racks. We then develop ideas for improvement, followed by creating the geometry, generating the mesh, and applying boundary conditions. Then we tested those ideas individually through thermal simulations and structural simulations, and finally did a fatigue analysis. We then examined how those ideas perform all together to create our final design and adjust changes based on the performance of each design. The method used was brainstorming ideas after the constraints were considered. Some of the constraints included the size of the furnace. We did not want to make the racks taller, or we did not want to increase the weight of the racks because it will use more energy in the furnace. So some of the ideas we consider was changing the hole distribution as seen in the figure on the screen. We consider applying a shaft structure to the top, changing the platform configuration, increasing the beam thickness, and yes. So now this method generated 12 design ideas, which led to 25 FEA simulations for each individual change. So our results in the following slides, we'll present some of our most impactful designs. We'll start with the upper rack. The upper rack, we decided to change the shaft structure of the rack in order to improve the the heat flow from the furnace into the coils. This also resulted in a weight reduction of 24%. The maximum equivalent stress was reduced from 1300 KSI to 1200 KSI. But we can still see a lot of stress areas in the CAD model. So this design, even though it's good, it still doesn't prevent high stress in the rack. Another design was changing the upper rack hole distribution. Now, this design also was focused on improving the airflow through the rack since it's at the top. This design resulted in a 1.8 weight reduction and reduced the stress significantly from 1300 KSI to 1100 KSI. Another impactful design for the upper rack was adding holes to the lift beam. Now, adding holes was also intended to increase airflow. This did lower the weight of the rack by 2.5%. Even though it increased the stress, we're still reducing the weight and improving the rack overall. Now I'm going to pass it over to my partner, Joe Madrigal, who's going to talk about the changes we applied to the lower rack.
Hello, everybody. So to continue on some of the ideas elaborated, one of the ideas we wanted to include was an increase in plate thickness on the lower rack. Now, we did do this with an additionally 0.5 inches, but we found that the relationship between as we increase the weight, the stress reduces. So with weight increase, it's a problem because it increased the cost. So to minimize that, we only added just 0.1 inches, and that yielded, even though very minimum weight increase, it did reduce the max stress and improve the stress distribution across the rack, as well as reducing the stress value for the cyclic stress value of 2300 KSI to 2200 KSI approximately. And again, once elaborated before, we also added the hole in the lift beam idea to the lower rack, which did reduce the weight in the individual lower rack, just as it did for the upper rack, but it also decreased the maximum stress of the lower rack from 2300 KSI to around 2000 KSI. And the last idea we also included was a change in hole distribution. We really made this idea to subject to more heat flow going through the rack, as well as possibly allowing the stress distribution to be more less concentrated. And even though it slightly increased the weight by 0.9%, we did have very curious stress reduction, while which essentially distributed the stress evenly in critical areas where failure is common, as reported by the engineers in the industry. And this change also reduced the max stress from around 3000 KSI to 2000 KSI. And here we have is just a summary of all the design ideas. What we did was, after taking all the design ideas in consideration and finishing their simulations, we determined whether they passed the criteria, which we deduced these were the criteria for the most effective, for having the most effective design, again by approval by the engineers in the industry, which was the reduction in metal, the distribution of stress concentration, the reduction in the stress reading, and also, if possible, allowing for more heat flow, as shown in the images. In addition, more ideas are as follows. But overall, we were successfully able to create a final design that allowed for more heat flow to flow through the plates, as well as distributing the stress across the racks, specifically the lower rack, which again is where failure commonly occurs. And in addition, we also to minimize the weight, specifically in the upper rack, which again linearly affects the increase in stress in the lower rack. And to perform a fatigue analysis, we wanted to see the performance across the entire rack for how many cycles each part would show before failure. Even though there are some areas, such as the corner of some holes that you can see in the lower rack to the left, there are some critical stress areas in the notch areas. But overall, compared to the original, this did have minimal or significant cyclic increase to allow for more for the rack to survive more cycles, broadly speaking. But in conclusion, the students were able to successfully examine the original design by a part-by-part basis using finite element analysis. And after designing multiple design changes, we chose the best performing changes that made a suggestive design for the industry. And this design was able to contain lighter mass, distribute dense stress areas where critical stress occurs, and to allow for more heat flow to go through the rack. Now, as for future work, we really recommend that some of the researchers that work on this project further to potentially use a computational fluid dynamics simulation, which is a simulation that could show the heat flow throughout the rack, because in the actual furnace, the heat flows from the top of the furnace down to all the way through the rack down to past the lower rack. So if that could be simulated, that would be extremely helpful. In addition, we'd like to note that there are changes that could be made to the rack, but also it would require consideration due to the machinability and material costs, such as a less customized part. If a less customized part were to be ordered, then it would be cheaper than a part that is customized. And also to point out that the main beam channel is a particular area for improvement, in addition to the design ideas that we have. And we also like to note that some ideas, such as a unified piece of the rack or the plate and the platform structure, what showed is that it potentially had an extremely improved structural performance, but the trade-off is that the manufacturing is going to be essentially more difficult with material costs and just being realistic in that case. Okay. We'd like to thank the engineers in the industry for supporting this project. We'd like to thank the members of the Steel Manufacturing Simulation and Visual Consortium. And we'd also like to thank our fellow researchers at Civis for giving us the tools to allow us to continue through this project. At this point, we'd like to thank you for listening today, and we'd be happy to answer any questions you might have.
Any questions? All right. Thank you very much, gentlemen. Great job. Great presentation. And so we'll move on to our next presenter. This is Justin Abella from the University of Toronto. And Justin is talking about the impact of COVID-19 pandemic on the global iron and steel markets.
All right, fantastic. Let me just turn on my camera here. Can you all see me? Can you all hear me?
Yes.
Yes.
Okay, great. Let me just share my screen here. Here we go. How does this look for everyone? Okay, I guess we can get started. So, hi everyone. My name is Justin Abella. I am a material science and engineering student from the University of Toronto. And today I'll be talking about the impacts of the COVID-19 pandemic on the iron and steel industries in China, North America, and the global markets. And if you were wondering what this picture is over here, this is actually from the Dofasco plant in Hamilton, Canada, which is very close to Toronto, up here in the north. So in this presentation, I'll be giving a little bit of an introduction and some background information about the markets previous to 2020. I'll go over some objectives I want to go over, the iron and steel industry in China, North America. Additionally, I will go over the iron and steel industry in the global scale. I'll talk about the future of the industry, then I'll wrap it up in some summary statements, some key conclusions, and I'll close off this presentation. And just a little bit about myself. If any of you can't see me on the webcam, this is me on the right, me wearing my graduation photo, and this is the U of T. And if you're wondering why I chose this picture, it's because I will be graduating in about 1 hour, which is exciting. But enough about me. Let's go on to the background information for the markets in 2019. So what were the markets like in 2019? So we know that China was the largest producer, consumer, and exporter of steel, with 53% of the world's steel produced, more than half of the world's producer. North America up there with 6%. And from World Steel, I've added this little table showcasing the tonnage of steel produced in 2018 and 2019 in these three countries, and additionally in the world. On the right, you'll see a sort of graph of the crude steel production from 1950 all the way to 2019. So from here, you see that as population grows, as population begins to expand, as projects begin to expand, the demand for iron and steel is obviously going to go up. So little bumps in the road, but you can see this ascending nature of the iron and steel market from 1950. But what else happened in 2019, can we ask? Then December 31st, 2019, as you all know, the first case of COVID-19 was reported in Wuhan, China. So my objective of this presentation is to analyze the effects of COVID-19 on the iron and steel industry. I went over what it was like before the pandemic, talking about the markets before 2020. And obviously the virus had hit. And now I'll be going over the markets in North America and in China just to scope down a little bit. And we want to analyze the effects on production and growth. And most importantly, how. How has the countrywide lockdowns affected the steel production and growth? From there, I'll talk about the world scale. And then lastly, the future of the industry. And with that being said, let's move forward. Start off with China. What was the production like in China? Well, there was a fall of production by minus 8.4% in February 2020. You can see this little dip over here. You can see the levels, average levels of 2019 were just about at this level before having a smaller little dip, excuse me, over here. But the full productivity of China had already recovered by April 2020 and is even higher than in the 2019 levels. In terms of growth, there is a little bit of variability with a decline of 6.5% in February 2020, but all the way up to October of 2020, that has already grown to about 12% year-on-year growth. Now you can ask yourself, why? Why has China recovered so quickly? Well, if you recall from last year, China had a relatively immediate reaction to the COVID-19 virus. They shut down their economies and their country very early on in January and February 2020. This allowed them to reopen their industry in March, giving them more time to bounce back from the pandemic. Now, Comparatively, let's look at North America. And what was the production like in North America? Well, there you see there's a 33% drop in the second quarter of 2020. And I added this little table over here showcasing the 2019 and 2020 million tons of steel produced in that time. But more importantly, I want to bring your attention to the graph on the right. Now, you see that United States, it being the bigger, the more impactful producer of steel in North America, you can see this obvious drop in March, April 2020. You can see this is the 33% drop. Now the growth here is a minus 15.7% decrease year-on-year growth. And again, you can ask yourself, why was this the trend? Well, a slower reaction to the COVID-19 virus kind of delayed the openings of the markets, delayed the opening of key steel plants. There was also a sharp manufacturing recession in the US around the time, and companies like Ford, Honda, closing their doors to prevent the spread, to encourage social distancing. But this has caused that drop of iron and steel around this time. So with that, we can talk about what the global trends in the world stage. I've added all of these little graphs, again, from World Steel, for the different regions of the world. And you can see there's a clear drop in early 2020 in the many continents on Earth. So the 65 reporting countries, there's a drop over here. Like I said, in North America, US, Mexico, and Canada, this drop over here in early 2020, Central, South America, China, obvious drop. But you can see that the reopening of the regions happened a lot in Q3. So you don't just see a sort of drop and stagnation around these levels. They slowly rose up after that crash in April 2020, after that lockdown, after that severe lockdowns in April 2020. I think it's important to note what the World Trade Organization is reporting around this time. And you can see that global trade fell from minus 5.3% in 2020, hitting a low in Q2. And it's obvious when you see this rising trend over here, whereas this immediate fall in Q2 of 2020. But there's a steady increase, and I wouldn't even say steady, I would say a rapid increase after April 2020 in the third quarter of that year. So you can see that the trade has obviously been kind of correlated to the iron and steel markets around that time, but this recovery is very analogous to the iron and steel markets. Now you can see this dotted line as the forecasts, and it is also in this ascending nature, in this ascending pattern. So we can expect an already recovery from the iron and steel markets. So let's go about the production again, this time on the global scale. There's a minus 2.8% decrease in production. And you can see this is clear with this drop from March to April. And just a little note that I have included the graph from the rest of the world, not including China, because of the fact of China being such a large producer of the world, such a large chunk. So I think it was a bit more, it gives us a bit more perspective on the rest of the world if we didn't include China in this map. But again, as I was saying, there's this obvious drop in March to April 2020 with a steady increase after April. This steady increase, this steady, again, ascending nature. Now the growth has seen a minus 30% drop from February to April. Again, very obvious. Start from here, goes down, a minus 2% year-on-year growth at the end of 2020. But again, this ascending growth, and already at the end of the year, we see more of a positive year-on-year growth over here. Now, this is a trend, as I was saying, as countries reopen their economies in the third quarter of 2020. We see a slow recovery with a positive percent growth after October. But even so, there have been closures in major steel plants around the world. Now, I've added a few of these steel plants that have closed down their doors to encourage social distancing and to limit the spread. British Steel, Tata Steel, Nucor, but there are reports that in the year 2021, we will see a recovery in new capacities at companies like Nucor, Steel Dynamics and Big River Steel up in North America. So when can we expect a return to normalcy? Well, I would argue that we're already on the way. You've seen the rise in the global trade. You see the rise in production and growth. As vaccines roll worldwide, the world will continue to reopen, and the decline in the global COVID-19 cases as of June 21 has seen this declining nature. So obviously this is a tragic event, but we are seeing a kind of lowering of global confirmed cases. And with this, as more projects begin to open and resume post-pandemic, the demand for steel and later the production of steel will continue to rise again. So let's talk about the future of the iron and steel industry. And I've added this little table showing you the forecasts of the iron and steel industry. And especially in these highlighted areas, we can talk about the different regions that I talked about in this presentation: North America, the world, and China. Now it's obvious you can see that in 2020, we see a negative growth, a negative year-on-year growth rate. But in 2021 and 2022 forecasts, we can already see that we see positive growth rates. We see recovery, which is very promising for the iron and steel industry. As the world moves past the pandemic, the industry would continue to grow, which is incredible. So the future of the iron and steel industry, according to the Iron and Steel Mills and Ferroalloy Global Market, we see that in 2020, we see an $820 billion market cap with a forecasted rise to 870 billion, and all the way to 2025, 1.14 trillion, which is just on that path to growth. So with that being said, let's give a little bit of a summary of what I went over today. So in China, we have a max fall of production about minus 8.4% in 2020, a decline of minus 6.5% in year-on-year growth in February. But we know that because of these early lockdowns, markets reopen a lot quicker. That allowed them to produce steel at a higher rate, at a more normal rate than the rest of the world. In North America, we saw this 33% drop in production at the start of the lockdowns, and the recession in March caused much unemployment and closures in industries that require iron and steel, kind of lessening that demand for iron and steel. And obviously with lesser demand, there's lesser production. And the delayed lockdowns delayed the opening of the economy. But on the world scale, we see a minus 2.8% decrease in global steel production, a minus 5.3% decrease in global trade. But with all of those graphs, we see a slow recovery in 2021 as markets begin to reopen again. So some key conclusions here is that the COVID-19 pandemic has obviously caused a decline, and that the industry recovering as these sectors that demand iron and steel, such as construction and automotive industries, reopen their economies again. And we also have maybe a projected V-shaped economic recovery. What does that kind of mean? Well, I'm going to bring up this sort of chart again, and this one is updated to 2020, not 2019. And you can see as steel grows, as population grows, the demand for steel grows, and there are always bumps in the road. It goes down, but it always rises back up. For example, right here is the 2008 financial crash with this dip, but obviously it goes right back up, dip right back up, this V-shaped recovery. Now right here, we can see this obvious little dip or this little stagnation, and it can be predicted that this stagnation is the pandemic, whereas the recovery, as it has been in the history of the human race, at least since 1950, the recovery will see a growth once again. And just as a disclaimer, this is a forecast based on historical trends and is not meant to be considered as factual. And I just wanted to end off with a little saying from the Iron and Steel Mills and Ferroalloy Global Market, is that the COVID-19 pandemic was obviously an unforeseen event that did halt the iron and steel industry. But these shutdowns are not at all related to any ongoing fundamental weaknesses in the market or the global economy. And we can see that with the with the growth, with the recovery of many of the regions around the world. And because of this, hopefully we will see the industry thrive once again. So with that, I just want to thank you all for listening to my presentation. I hope you gained a little bit of understanding of how the pandemic affected the industry. And I hope you all stay safe during this time. Thank you.
Very good, Justin. Thank you very much. Any questions for Justin?
Hi, I have a quick question for you, Justin. Can you all hear me?
Yes, I can.
Yes, we can. Thank you.
Great. I was curious if you'd done any kind of breakdown in terms of the, here in North America, we have the kind of two wind approaches to iron making. You have your integrated mills versus mini mills. Did you do any breakdown on kind of what impact there was on the integrated side of things versus the kind of EAF method that's become very popular over recent years? Has there been any kind of different impact, or was it kind of uniform?
I really didn't look into the into that impact of mini mills or EAF. I do know that at least in the terms of blast furnaces around the world, they did have to shut down a lot. But in terms of mini mills, I really don't know the specific details for that. So.
Okay, thanks.
Okay, Justin, thank you. Our next presenter is Gabriela Jacinto, and she's from the Federal University of Minas Gerais, and her paper is functionalization of vegetable lofa for boron and chromium absorption of industrial wastewaters. Thank you, Gabrielle.
You're muted, sir.
Gabrielle, you're muted. We're not hearing you.
Can you hear me now?
Yeah, Gabrielle, there we go. Thank you.
Okay, thank you. Good morning. So, can you hear my presentation? Can you see the presentation already?
Yes.
Yes.
Okay. Good morning. My name is Gabriel Jacinto. I am an undergrad student of chemical technology at Federal University of Minas Gerais here in Brazil. I'm going to present my undergrad final thesis, tutored by my bachelor's advisor, Professor PhD Marcelo Machado Viana, from the chemistry department. And this project is called functionalization of vegetable lofa for boron and chromium absorption of siderurgical industries with water. This presentation will be summarized in introduction, bibliographic revision, goals, and materials and methods. Hydro resources are important for almost all industrial processes and for life in Earth. The water can be used during the production process or even the final product. As a result, the wastewater can be contaminated in most of the cases. Their disposal are incorrect. Siderurgical industries, for example, use water to cool down the steel and perform surface treatments to improve the steel properties. In most of the cases, additives are used to improve the efficiency of the treatment performed. It was common that a central sewage treatment plant were used to treat all the wastewater from the industries and from the cities. This is not good because the complexity of the wastewater of the industries increases the difficulty to treat the water and release a better quality water in the environment. In this example, the industrial wastewater is treated inside the plant and the final results are quite better. Siderurgical industries use boric acid as a lubricant mechanical conformation process and chrome in electrochemical baths to increase mechanical resistance and avoid corrosion in the steel. Even after regular wastewater treatment, the substance can be found in trace concentrations in the treated water. Remove these trace concentrations is really hard and new technologies are necessary. Chrome is well known to be carcinogenic when ingested, and it's bioaccumulative. In other words, after ingestion, it accumulates in the body tissues. The boron, for example, if it's in high concentrations in the soil, can cause deformations in plants and necrosis, and even can devastate an entire plantation. To avoid such situations, governments around the world started to create laws and rules to control better the destination of wastewaters. In Brazil, for example, the CONAMA, Council of National Environmental, limited the concentration of the substance allowed in the wastewater after the treatment. The total boron is allowed only below 5 ppm concentration. The trivalent chrome is allowed only below 1 ppm concentration, and the hexavalent chrome is allowed only below 100 ppb of concentration. The lowest value for hexavalent chrome is because it's known that this kind of chrome that must cause carcinogenic effect. Remove substance present in trace concentrations, as I said, is hard, and adsorption is a well-known method capable to such thing. Here is an example of possible use of adsorption technologies for the treatment of wastewater. Inside the treatment plant, it's possible to use filters with adsorption technology to remove the trace heavy metals in the water and release that treated water to the environmental. Here is a quick review about adsorption. Adsorption is the interaction of a substance called adsorbate with the surface of a solid known as adsorbent. These interactions happen by physical interactions in case of physisorption, where this adsorbate, these molecules, get proximity to the adsorbent, and then by difference of potential of electricity charge, they get and form multiple layers in the surface of the adsorbent. They can fill the pores too and get into the adsorbent structure. But there is a possibility of chemisorption too, where a vacuum binding bond site reacts chemically with the adsorbate and holds in a unique layer on the surface of the adsorbent. It's possible that both of the adsorption occurs. First, the adsorbate chemically react with the vacuum binding site. Then, by physisorption, other layers can be formed and fill the entire pore. The adsorption efficiency can be improved with treatment made in the adsorbent surface, process that we call functionalization. One interesting property of adsorbents is that it's possible to recover the adsorbate through a process called desorption. Then you can use again the same adsorbent. Adsorption with coal and clay is widely used. Even inside our homes, these materials are used, such as in water filters. This is an example of a clay water filter filled with activated coil to filter the water here in Brazil. However, the process to obtain these materials can still generate environmental impacts, as produced coil is needed to burn wood in a very specific condition, and the clay mining creates such big impacts as another kind of mineral extractions. Biosorption, in other hands, mostly use vegetable fibers, which can be prepared for almost any fiber in the nature. Here are examples of coconut fiber, loofah fiber, and sugarcane bagasse fiber. They are cheaper, have operational low cost, high selective capability, and it's possible to recover the metallic species. Furthermore, they are biodegradable and easier to correctly dispose after reach the use life. In this example, coconut fibers were used to adsorb heavy metals present in water. Coconut fibers are composed by 23 to 43% of cellulose and 35 to 45% of lignin, and this composition is very important for the adsorbate characteristics. A study of the zeta potential variation in different pHs performed to evaluate the charge behavior in the coconut surface. In high pH values, the values tend to fall, showing that there is an accumulation of negative charge in the surface of the fibers. As you can see, in the lignin and in the cellulose molecular structure, they have a great amount of hydroxyl groups. These hydroxyl groups tend to lose the hydrogen in higher pH values and consequently stay with an unbonded oxygen with a negative charge. In theory, this negative charge should attract metallic ions present in wastewater to the fiber surface. In this graph, the adsorption capability of the coconut fiber in the pH range are present for some metallic ions. The hexavalent and the hexavalent chromium and the cadmium between the pHs 3 and 9 tend to absorb more in this range of pH, but the bivalent, the hexavalent chromium tends to drop its adsorbent capability with the increase of pH. This falling volume indicates that there must be having competitions for the binding sites in the fiber surface between different type of ions and that are forming high pH values. Furthermore, metallic ions tend to form complexes ions when they are in some pH range values, when you increase the pH. Here is presented two images taken using scanning electron microscope. It's possible to see that the adsorbent particles are porous, but there are presence of smooth surface too. This is important because big adsorbate particles tend to adsorb by weight transfer or physisorption, accumulating the pores, and smaller ionic adsorbents tend to chemically interact with the adsorbent surface, having a chemisorption. The presence of both types of surface in the adsorbent increases its capability to absorb different types of ions present in the wastewater. The Langmuir isotherm and the Freundlich isotherm were constructed to evaluate the best fit for all the adsorptions. The bivalent cadmium and hexavalent chromium were best fitted by the Langmuir isotherm, while the trivalent chromium was best fitted by the Freundlich isotherm. Were found that all adsorptions were favorable, showing that the coconut fiber is a good adsorbent. Now, talking more about the loofah, principally the Brazilian sponge gourds, we found that the composition of the Brazilian loofah is close to the coconut fibers. The composition is based on cellulose and lignin. And these structures allow the surface chemistry to be changed, increasing the adsorption and selective capability. Here's a picture of the fiber of the loofah. In the picture A is the untreated loofah, has a thick layer of lignin in its surface, blocking the pores and cellulose fibers. With the addition of sodium hydroxide, the lignin is removed. And here in figures B, C, and D, the concentration of sodium hydroxide is the same, but the time of treatment are different. We can see in figure B that there is a good removal of lignin of the surface, exposing the pores of the cellulose fiber. In figure C, there is a more exposition of the pores, but in figure D, with 90 minutes of exposition, the fiber starts to get destroyed, and this is not good for the absorption of the metals in the wastewater. The loofah fibers were treated with metacrylamide 2. In figures A and B, it was at 1% concentration for different times, 120 and 180 minutes. And in figures C and D, they were treated with metacrylamide at 3% of concentration and for the same times. At low concentrations, you can see that the pores are evidenced, but for higher concentrations, the metacrylamide starts to destroy the fiber too. And with low concentrations and 180 minutes of treatment, the surface of the loofah fiber starts to be smoother, which is good to attach another kind of chemical compounds in the surface to increase the adsorption capability. In this figure, you can see the infrared spectra for the loofah fibers when it's untreated in the letter A, treated with sodium dioxide in figure B, and with metacrylamide in figure C. We can see that there is a change in the spectrum, confirming that the structure of the surface were changed with the functionalization. The goals of this project is the functionalization of the vegetal loofah by the alkalinization and impregnation of citric acid to improve adsorption capability for boron and chromium of the steelmaking industries. So we plan to do the evaluation of the vegetal loofah adsorption capability in its natural state, the functionalization of the vegetal loofah by decolonization, impregnation, and the characterization and evaluation of the influence of the pH in the boron and hexavalent chromium adsorption. This last is very important because it's difficult to control the pH of the wastewater in the industries. So provide adsorbent that's able to work in that pH range is very important. These are the materials and methods that we plan to use. Unfortunately, we weren't able to do any of the experiments in laboratory due to the pandemic situation here in Brazil, as the laboratories at universities are closed for undergrad students. Finally, I want to thank you, the AISTech, for the opportunity to attend the contest virtually. All the members from the UFMG student chapter for all the support, principally Professor Ronaldo, Professor Marcelo Machado Viana to have accepted my bachelor's advisor, the Federal University of Minas Gerais and the chemistry department for all these years of great education and structure provided during the bachelor's degree, and for our sponsors, JMN and Cassotes, for believing in the power that students have to change the world.
Thank you, Gabrielle. Questions for Gabrielle? Okay, thank you, Gabrielle. Our next presenter is John Roser and Emily Higley from Purdue University Northwestern, and their presentation is Design of Oxygen-Enriched Combustion in a Reheat Furnace.
I can't share the screen while someone else is. Thank you.
Am I visible? Okay. Let's see if I can get this
Oops.
sorted.
Hold on, this is the wrong slide.
Here. See if I can.
Are you good, Emily?
I'm working on it. I'm getting my camera adjusted. And let's go to move. All right. Should be relatively effective.
All right. So my name is John Rosser. My partner's name is Emily Higley, and our project is titled Design of Oxygen-Enriched Combustion in a Reheat Furnace. So this is our presentation outline. We're going to start with an introduction, which will consist of the background, our motivations and objectives. We will explain our methodology, our results, and then have a discussion, including topics such as the slab heating profile, NOx emissions, and cost analysis. Then we'll go over our conclusions. So some background on the steel industry. If you look to the right, you see an image that explains the overall steelmaking process. We start with iron ore, limestone, coal, or scrap metal. These materials are processed to make molten steel. That steel is then poured in a process known as continuous casting to create semi-finished products in the form of blooms, billets, or slabs. These products are moved into a reheat furnace to prepare them for rolling so they can be rolled down to the desired size for whatever product you're making. Now, in 2019, the US steel industry created 87 million tons of steel, which equates to $92 billion worth. Our project focuses on the reheat furnace portion of the steel making process, which heats slabs so that they are more ductile so that they can be rolled down to the desired size. This is the second most energy demanding step, consisting of approximately 36% the energy of the entire process and equates to 24.5 megajoules per kilogram of steel. So then this leads us to our motivations, which the high energy demand of the reheat furnace leads to high energy costs for the steel mills. Nitrogen carries much of the heat out of the furnace and away from the slabs. You can see in this image below, it explains it very nicely. Air, which is composed of oxygen and nitrogen, along with fuel, are injected into the burner and combust within the furnace. Heat from the combustion moves to the slab where we want it, but also out through the flue gases primarily carried away through the nitrogen. We can decrease this nitrogen by increasing oxygen, and this is known as oxygen enrichment. This reduces NOx emissions and improves our fuel efficiency. Increasing the fuel efficiency through oxygen enrichment could lead to significant energy and financial savings for the mills. So then we outlined our objectives, which are to use computational fluid dynamics to model the flow and reactions within the furnace, to design oxygen-enriched combustion that maintains an acceptable slab heating profile. We want the slab heating profile to be relatively uniform. That way the properties within the slab, such as ductility, are uniform. That way they can be properly rolled. We want to reduce NOx emissions produced from combustion within the furnace and perform a cost analysis on the fuel and oxygen consumption to determine the economic viability of oxygen enrichment. We first started conducting the literature research that guided our decisions. We created an ANSYS Fluent. We used ANSYS Fluent CFD software to create a 3D steady state model utilizing the K-epsilon turbulence, species transport, eddy dissipation, and discrete ordinate radiation physics models. Our furnace was the geometry for our furnace was supplied to us from previous Civis work. The slabs in this furnace are moved through the furnace by a walking motion of rotating arms. This makes this type of furnace a walking beam furnace. It has 5 zones: a preheat, heating zone 1, heating zone 2, intermediate zone, and soaking zone. The green and yellow dots you see along this furnace represent the burners where combustion takes place. To heat the slabs, which are shown in blue, the slabs enter through the left side, move through each zone, and exit through the right. Me and my partner, we focused on modeling the bottom intermediate zone of this furnace. The ceramic skids that the slabs rest on are shown in gray, and the skids and the slabs are shown in blue. The tabs along this portion of the furnace represent the location of the burners. We placed oxygen ports in between the burners, and we did this because the existing burners cannot be modified. And we chose to do this because geometrically it made sense to place them in between the burners so that we could try to have even heating of the slabs. The port size is dependent on the oxygen enrichment and fuel percentages. Oxygen is also injected at sonic speed because we want the reaction to take place deep into the furnace and away from the burners. And we also want to keep our oxygen fuel ratio constant. Now, these constraints are important and determine the diameter size of the ports. So me and my partner created a MATLAB script to calculate the diameter for any given oxygen enrichment percent and fuel percent. So we studied 8 cases. The first case is a baseline case, and the cases are defined by the O2 mass percentage of oxidant and the mass percentage of the original fuel. So in case 1 being the baseline, 21% O2 mass percentage just represents that we're just injecting air into the furnace. 100% means this, well, this is the baseline, so it's 100% the fuel compared to the baseline. That makes sense. So then for the rest of the cases, for the O2 mass percentage of oxidant, this includes the O2 mass percent of the air combined with the additional pure oxygen being injected. So cases 2 through 4, were low oxygen enrichment levels, so a 40% oxygen mass percent, and the mass fuel percentage varied from 50, 80 to 90%. Cases 5 through 8 were medium oxygen enrichment levels at 60% O2 mass percent, the total oxidant, and we varied the mass percentage of the original fuel 50, 60, 70, and 80%. I will now be handing over the presentation to my partner, Emily.
All right, thank you, John. Let me make sure I can get this working. Perfect. All right, so this slide shows the flame shapes for the baseline case. So the flame shapes were created using a very small carbon monoxide mass fraction. This was done because carbon monoxide is a product of the combustion reaction that we considered. So this allowed us to essentially see the shape of where the combustion was occurring. The flame shapes are colored by temperature, so we're able to see how hot they are. And an isometric view is shown in the upper left. This allows us to see where the flames are located within the fluid region considered. A side view and top view are also shown. I will be showing a comparison between the baseline case and the optimal enrichment cases, one within each enrichment level category, based on heat flux, which we'll discuss a bit later. So here we can see a top view comparison between the flame shapes for the baseline case, case 2, which was the optimal low enrichment case, and case 7, which is the optimal medium enrichment case. The zoomed in view here shows where oxygen ports were located relative to the burners. And one of the main things that we can immediately note from this is the lower temperature flame bank occurring all along the burner wall. So this occurs due to the fact that oxygen is not only injected at the burners for these cases, but it is also injected in between them at the ports, so the flames are able to mix. Another thing to note, and this is more evident in the low enrichment case, is that the flamelet shapes characteristic of the baseline do again occur further into the furnace. However, they actually occur in line with the oxygen ports rather than the burners, and this is due to the high oxygen velocity. One more thing we can note about that mixed bank occurring near the burner wall is visible here from the side view, and that is that that flame shape actually spreads upward rather than simply being injected straight into the furnace like the flame shapes of the baseline, and this is due to reduced fuel momentum. This slide shows a comparison between a horizontal burner and port midplane within the fluid region, and we can see the baseline temperature. We have higher temperatures occurring near the burners, whereas for the enriched cases, we do not have as many high temperature regions occurring. Those that do occur start further into the furnace and are in line with the ports. However, the moderate temperature area, and it may be a bit difficult to see, appears in yellow here, and we can see for both of these cases it actually extends all along the middle of the fluid region, all the way through the furnace, whereas for the baseline case, moderate temperatures tend to occur closer to the burners. This shows a comparison between fluid flow behavior along a vertical plane intersecting one of the burners for the baseline and the two optimal enrichment cases. One of the main things to note here is that higher turbulent effects occur for the enriched cases due to the high velocity with which oxygen is injected. And this is positive in the sense that it promotes mixing for the enriched cases because a lot of the oxygen is injected further away from the fuel than it would be for just the air-fired burners. This allows the fuel and oxygen to mix in a way that is then comparable to the baseline case. So this slide shows a comparison between the heat flux leaving the fluid region and entering the bottoms of the slabs for the baseline and the two optimal enrichment cases. The main thing to note about this slide is that these were the enrichment cases that were found to be optimally comparable within their categories to the baseline heat flux. And as John stated earlier, this is important because uneven heating can cause uneven temperatures of slabs, uneven properties, and damage can occur when slabs are further processed. So this is very important. This table simply summarizes the last slide, showing that optimal heat flux occurred for case 2, which is the 50% fuel case within the low enrichment level, and case 7, which is the 70% fuel case within the moderate enrichment level. So for NOx emission, the main thing to note here is that for oxygen, a larger percentage of oxygen is included in the oxidant relative to nitrogen, which means that there is less potential for NOx to be produced simply because there is less nitrogen. And as we can see, based on our simulations, less NOx was produced in both cases 2 and 7, with the greater decrease occurring for the lower enrichment level. This shows a loose estimate of operation cost based on fuel price and oxygen price per hour, just so we can show that savings do occur with oxygen enrichment, with a higher saving level occurring for the low enrichment case. And this table summarizes cost savings and NOx emission decrease so that we can see that the low enrichment case was found to be optimal based on our simulations. So in conclusion, fuel consumption and NOx production can be reduced through oxygen enrichment, and this can be conducted in an economically viable manner. And lastly, based on our simulations, the optimal approach to this is a low enrichment level with 50% of the original fuel, leading to an estimated 33% cost saving and 57.5% decrease in NOx emissions. Lastly, we would like to acknowledge the support of our mentors and advisors, Dr. Zhao, Dr. Silene, Francisco Martinez, and we would like to acknowledge funding from the PNW Undergraduate Research Grant and the India Space Grant, who provided the necessary funds for this research to be conducted. Thank you for your time. Any questions?
Okay, thanks, guys. Appreciate that very much. We'll move on to our next presenter, which is Bernardo Moriella, which is optimization of the production scheduling in a seamless tube rolling mill plant. And he is from UFMG, Brazil.
Yes, good morning. Can you hear me? Everything okay?
Everything's okay.
Okay, thanks. So good morning, everyone. My name is Bernardo Moreira. I'm a production engineering student at Universidade Federal de Minas Gerais here at Belo Horizonte, Brazil. And I'm going to present my project, Optimization of the Production Scheduling in a Seamless Steel Tube Rolling Mill Plant developed at Valorec. First of all, I'd like to thank AISTech 2021 and our judges for this opportunity of the presentation. And I'd also like to thank Valorec for my internship there, coordinated by Professor Ronaldo Sampaio and also Rafael Correa. This is a software project developed by the operations research team at Valorec's Technology of Automation sector, where I work. And this is also the story of how we've used Charles Darwin, some bows and arrows, computer programming, and our expertise to create a result of an 18% cost reduction and a 30% setup time reduction in one of the most complex production lines at the company. So why is it the rolling mill so complex? Because there are machinery setups at the rolling mill that are huge and very expensive. The tooling changes there are very hard and they compromise quality. So when the number of setups goes up, costs also go up, productivity goes down, and quality also goes down. This is so relevant that there are some employees at Valorec that take full days to come up with the best schedule that minimizes the number of setups each month that they can do. So am I really saying that we're going to use Charles Darwin, bows and arrows, computer programming, and ourselves to create this result in one of the most challenging environments in the company? Well, yes, and now I'm going to show you how. So the first thing we should be aware of are some specifications of the seamless steel tube. So some of the main visible specifications of the tube are its length, of course. It's outside the emitter, which I'll call OD. It's inside the emitter, which I'll call groove, and the wall thickness, which is the difference between the OD and the groove. The OD and the groove will be the most important specifications for us, and they will impact directly our result. Taking it to the rolling mill itself. The rolling mill looks something like this. Of course, it has rolls that roll and press the billet. So the billet is moving to our right, and it's hot, it's massive, but it's being perforated by a mandrel. So the billet is being transformed into the tube itself. In the rolling mill, there are those very important and also very expensive tools called stands. The stands are tools that come outside of the tube to maintain its position, and they are specific to the OD and to the groove of the tube. Meaning, every time we sequence consecutively two orders, two tubes that don't have the same value of OD or the same groove, then we have a huge setup. We have to change the stand, and we lose all its remaining lifespan. So every time we talk about sequencing consecutively, we're talking about production scheduling. So production scheduling happens when we have a make-to-order approach in which all orders shall be scheduled, let's say in a month. So the task is to determine the best sequence of orders to be processed. But what is it that determines which sequence will be the best? Which are the criteria? Well, sequencing consecutively orders that don't share specifications requires machinery setups. As I've said, machinery setups have financial and time costs. But the thing that really complicates our situation here is that all orders have release dates and due dates that shall be respected. So let's take a look at some balls and arrows, as I've called example, or nodes and edges. Let's imagine that we have two nodes, green nodes, that represent the orders O1 and O2. They have an outside emitter of X. And let's say also that we have two nodes, yellow nodes, O3 and O4, that have a different outside emitter, let's call it Y. So if we sequence those nodes in this manner, O1, O3, O2, and O4, every time we change the color in a sequence, we have to make a setup. We have to change the stands and change lots of other specifications of machinery. So we have three setups in this case. But if we rearrange the nodes in this manner, O1, O2, O3, and O4, we bring together those which share color or the outside emitter or the groove, some specification. Then we only have to do one setup. So this is good for us. And the same is true for the case of the tools. If we use the previous sequence, O1, O3, O2, and O4, we have to use 4 different stands, one for each order that we sequence. And then we'll lose 4 remaining lifespans. Each time we change a stand, we lose all its remaining lifespan. But if we, again, bring together those nodes with the same color, then we will only use 2 stands, one for each color, and in the end, we only lose 2 remaining lifespans. But as I've said, the thing about due date is really what complicates our situation. Let's imagine that each order takes a day to be processed, and we have the following due dates. The green balls, the green nodes, are due to the day 4. And the yellow nodes, they have tighter due dates. They have day 1 and day 3 as due dates. So if we schedule these orders in this manner, we'll respect the setups and the tools requirements. We'll have the optimal solution for them, but we won't be respecting the due dates of the yellow nodes. If I change the way we order the colors, we can produce the yellow nodes first. They will respect their due dates, and also the green ones will respect the due dates. But that's quite not what happens in reality. It is far more complicated than that. And one example is, imagine if this O1 green node doesn't have the due date as day 4. If it has due date as day 2, then it is simply impossible. It won't be possible to get the best setup scenario and respect the due dates, because I want to do the O3 in day 1 and the O1 in day 2. But if I want to optimize the setup, then I want O4 to be close to O3. And this happens a lot and a lot of times. So to take a look at the real complexity here, I brought a table that shows the number of possible solutions for a scheduling problem, and it isn't linear. So taking a look at 4 orders, as we've been doing, we have 4 factorial possible solutions, which results in 24 final options. Okay, us as human beings can look at 24 final options, evaluate every single one of them, and choose the best. That's not something complicated to do each month. But if we raise this number up to 10 orders, then there are 10 factorial possible solutions, which results in more than 1 million final options. Well, this is getting a bit out of hand for us to list all the options and choose the best, evaluate everyone and choose the best. If we take it to 20 orders, then there are 20 factorial possible solutions and something like 10 raised to 18 final options, which shows that it is completely impossible for us human beings without computer aid to evaluate every single order and choose the best. So the million-dollar question is, how do you find one solution in 10 raised to 18 or more? Well, the answer is optimization. What is optimization and how do we do it? The optimization is, by definition, the action of making the best or most effective use of a situation or resource. In our case, it means finding the schedule that minimizes production costs and setup times while respecting due dates. And as we've seen, those are sometimes conflicting objectives. And we do it nowadays through a genetic algorithm, or a GA. So the GA was first developed by John Holland in 1984, and it is simply a sequence of steps that we tell the computer to do in order to create and choose new possible solutions. We created our own GA with Python programming language, and even for a computer, it is impossible to look at 10 raised to 18 possible solutions or more and choose the best. So we get some good solutions and we improve those solutions step by step. The GA is called genetic because it simulates the process of natural selection proposed by Charles Darwin. First of all, we have fitness. We randomize some good solutions, and then each solution is evaluated, meaning we calculate how much time and costs would it imply if we took it to production actually. Then we rank those solutions based on this fitness and make the selections. The best solutions will survive to the next phase, which is the creation of the offspring. The offspring is creating, mixing, and randomizing parts of old good solutions. This loop goes on and on and on, and after many iterations, a near to optimal solution is found. Currently, we have a 10% average gap to the optimal solution, which for our situation is quite great. So how does it look visually, the GA? So we have some individuals, which are possible sequences of the orders that we can bring to production. Every one of them is evaluated, meaning we calculate the fitness about setup time, how much setup time we would have if we sequence the orders in this manner, and how much of tools cost we would have. Then we rank those solutions based on the fitness and some weights. The worst are discarded and the best are kept to the next phase of the GA, which is mating and offspring. We take 2 and 2 of the old good solutions, mix them and randomize just a little bit to create new non-identical solutions that we call offspring that will be a part of the next generation, and the loop goes on. After many iterations, the best solution comes to production. And this is the optimization of the production scheduling in a seamless steel tube rolling mill plant. The project results up to today In a 2020 data comparison with human-only efforts, the optimization resulted in a 30% average monthly reduction in setup times and an 18% average monthly reduction in production costs. So yes, Charles Darwin, bows and arrows, computer programming, and ourselves, we've done it. And the next steps are mainly keeping track of expected versus reality in monthly schedules, making small improvements in performance. They are important for the user experience. And of course, expand to other production lines. Nowadays, in Valorec, we also have this system for the steel plant, but there are many, many others that can benefit from this optimization strategy. So I'd like to thank everyone that helped in the development of the project and also the creation of the presentation. Of course, UFMG Student Chapter and its sponsors, AIST and Valorec. So if you have any questions, that's the moment.
Okay, no questions for Bernardo? Okay, Bernardo, thank you very much.
Thank
We'll
you.
move on. We'll move on to our next presenter, which is Alessandro Arellado from UFMG, and his presentation is Models Adjustment Report.
Okay, can you see my screen?
Yes, we can.
Okay. Hello, everyone. My name is Alessandro Azevedo Duarte. I'm an undergraduate student of Control and Automation Engineering at Universidade Federal de Minas Gerais, and I will present about the Model Adjustment Report. Talking about industries and concepts like Industry 4.0, points like the need for industry innovation, need for resource optimization always appear. Oh, sorry, I had a problem. I have a question about my video. Oh, okay. I believe I was not sharing my video. Yes?
We see you now.
We can see it.
Okay. I will restart, okay? Okay. Hello again, everyone. My name is Alessandro Azevedo Duarte. I'm an undergraduate student of Control and Automation Engineering at Universidade Federal de Minas Gerais, and I will present about the Model Adjustments Report. Talking about industries and concepts like Industry 4.0, points like the need for industry innovation, need for resource optimization always appear. The using of the latest technologies in industry can bring several gains in the production process, bringing gains related to full economy, quality of process, and better relationships of operators with the process as they will use tools to assist in their daily lives. Speaking especially of the steel industry, they have several resources to produce its final products. They have a complete environment to produce its product and several parts in this product, like the steel making, rolling, tempering, and the finishing process. And in each part of the process, we have a lot of materials that we can improve the usage. One of the main points of focus of this project is on saving resources, reducing the consumption of key resources like water, gas, energy, and fuels in general. With each passing day, we increasingly have a need for production quality assurance, whether in our production process or in solutions we will deliver for better customer use. In the industry, we have teams totally focused on digital solutions and interconnected with the quality sectors to deliver the best final product. This same industry is also experiencing a new steel era that not only steels are produced, but steel solutions. An increasingly present trend in the industry context is the artificial intelligence. Technologies like machine learning, data models, and mathematical models are increasingly helpful the operators to do the process. And an example is the mathematical model. But what is a mathematical model? The mathematical model is a simplified representation or interpretation of reality, which follows a structure of mental or experimental concepts. They are used worldwide in a lot of processes, and for sure at the steel industry. Speaking about the goal of the presentation, with mathematical models used in the steel industry context, with standards that can be defined worldwide or by specialists from each company, and with sensors to guarantee the process reliability, we can generate process improvements. To explain better the previous slide, with process standards plus mathematical models and digital data analysis, we managed to save resources and generate quality assurance, generating different types of gains for companies in the entire environment which it is inserted. Related to the approach, my proposal was to develop a digital solution for comparing real data with data estimated by the models. Speaking about my personal challenge, I had a lot of college learning. I learned how to program, I learned about databases, about instrumentations, about communication between different systems, and frameworks to help to manage the tasks like Scrum. And at Valorec, I had the opportunity to apply all these concepts and for sure learn more about the steel industry context. My project is a study of case using a mathematical model to predict the temperature of the tubes in a tempering process. But what is a tempering process? Tempering is a heat treatment process where materials are subject to high temperatures to modify their physical and mechanical characteristics. As shown in the graph, after the materials go through an austenitization process with a rise in a temperature and subsequent stabilization, and the process, it may or may not passes for a sudden cooling process. And after that, they go a tempering furnace and after cooling. At this project, the mathematical model named Sophia generates a standard heating curve. And this curve is so important because this is the real-time reference for the operators. As shown in this image, the object of the curve, it should be as close to the curve. The object of the pipes is to be as close as possible to the curve. And the blue dots are the ambient temperature that the model calculated in the specific position. And the green ones are the estimated temperature for that position. To resume the flow of the model, I resume the steps in the chart. First, we have the simulation definition for the better temperatures and variables. Second, we have experiences in the real process with online data in the model. And at the end, we have the utilization of the report to compare data and create the best adjustment. Speaking about the standards, for this project, the Valorec heat treatment community members helped me to define the best standards because they know a lot about the process and they know how to create the best solution for the clients. The senior engineers helped me to create the min and max deviations for the temperatures, the limits to soaking time, and the form to compare the curves and which type of material will compare with this report. Speaking about the sensors, the model uses sensors to make real-time calculations and show the temperatures forecast for the operators. One of main points of this adjustment report is a real tube with many sensors that is used like an example for specific materials. This pipe passes along the other tubes through the process and collect data throughout the furnace. we have the company named DataPack that provides sensors of this type, and with these sensors, we can check the temperature for the pipes in the furnace, like in this image. And it's important to say that this process is so expensive, and an adjusted model helps to save resources in this regard. Speaking about the report components, first, we have a production order drop-down that you can select the production order, or you can type the production order. And you need to insert the number of the tube that you want to compare. Each furnace has specific models, and you need to select the model that you want to compare. You can save a report and save the reports, and you need to select the simulation that you want to compare. Here, we have the buttons to save the report, delete an older report, or export this data to the Excel, and the folder to select which data pack you want to compare. We have two different systems for the variables. If you want to see the temperatures with Celsius, you can click in the international system. And if you want to see the temperatures with Fahrenheit, you can click in the imperial system. We have the specification of the plant and the equipment, and you need to select if you want to compare an austenitization or a tempering furnace, because they have different limits. And you can select if you want to use this thermal cycle as a base or as a verifier. We have a lot of information for the tube that you are comparing, like the production order, the date, the steel grade, and you have a summary with the temperature deviations between the model and the real process. The most important part of the report is the graph, a graph with a real tube trend calculated by the model, a simulation tube trend, a trend with data from sensors, furnace profile, roof and floor, limit curves, adjustment constants, and soaking temperature. Here we have an example of this report. First, we have the adjustment constants. For this report, we have two different zones, heating zone and the soaking zone. And these first curves are the reference curves. We have the furnace profile, soaking temperature, upper limit, and the lower limit. Second, we have the roof curve, the floor curve, and the simulation curve. After that, we have the real tube trend, the data pack channels, and the average between these two channels. And at the end, we have the different curve related to simulation, the real tube trend, and the heterogeneity curve. The difference curve is used to show these adjustment constants. Talking about the future work, the report is being validated and will be used in all plants in the group that use the model. In the future, the idea is to apply this report to other models to ensure quality even in different plants. To conclude the presentation, it is important to say that now the senior engineers have a complete solution to help them to take the best decisions, to generate process improvement, quality assurance, and to save resources. I would like to thank all of you for this opportunity, the AISTech, all the judges, and the institutions that I am connected to, UFMG, Valorec, UFMG student chapters, and all the sponsors, and the AIST. Thank you.
Thank you. Do we have any questions for Alessandro? Okay. Thank you, Alessandro. We're going to move on to our next presenter, which is Nicholas Reinheimer from Purdue University Northwestern, and it's the development of blast furnace simulator software package.
Okay, can everyone see my screen all right?
Yeah, we've got your screen and we can hear you.
Okay. Okay, good morning. My name is Nicholas Schreinheimer. I'm with the Center for Innovation through Visualization and Simulation with Purdue University Northwest. And today I'll be presenting my project on development of a blast furnace simulator software package. So blast furnace or direct reduction are the methods that can be used to make liquid iron from iron ore. In 2019, blast furnaces produced about 72% of iron used in North America. Electric arc furnaces account for a large amount of iron not made by the blast furnace, but that mostly deals with recycling iron, while the blast furnace produces new and higher grades of iron. So the blast furnace process consists of burden made up of alternating layers of iron ore and coke being packed into the furnace, where these orange segments represent the iron ore and the darker areas represent coke. Then hot blast enters through the lower part of the furnace through the ring of tweeters at the bottom. The coke and injected fuel combustion produces heat and reducing gases in cavities called raceways. The injected fuel, such as natural gas, for example, we've been working with hydrogen in our CFD cases, can generate heat and reducing gases, allowing for lower coke rates and lower costs. The residence time for the burden in the furnace is anywhere between 10 and 15 hours, while the residence time of gases is only between 10 and 15 seconds. So the blast furnace is the largest consumer of energy in the entire steelmaking process, which is mainly why we're focusing on trying to streamline the process and making it more cost effective. The previous CIVS work has produced simulations of a furnace under set conditions. And the motivation for the process for this project is, unfortunately, there are no current operations with cheap, quick methods of predicting effects of changes outside of known operating parameters, such as weather changes, shipment delays, and iron demands. There's not really a cost associated with CFD, but just a single TWEER case can take between anywhere between 6 and 18 hours. So the objective for this project is to develop a method to take blast furnace simulation data to produce a quick and accurate results of conditions, and then to present these results in an easy to use interface. So current CFD predictions indicate that it's possible to push additional natural gas while maintaining constant raft and top gas temperatures. The natural gas preheat will increase the raft, and it also reduces the predicted coke rate. This right here is our baseline case with no natural gas preheat and our standard natural gas injection rate. If you combine the natural gas injection rate, increasing it with preheat, you can see we can keep nearly identical raft and top gas temperatures with a lower coke rate per ton of hot metal, resulting in an annual $9.8 million in annual savings. So the methodology for our project can be split into two main parts. First, our CFD models, and then on to the interpolation model. The first step is the TWEER, which takes care of the iterative raceway shape, the coal combustion, coke combustion, gas combustion, and heat radiation. And then after that's finished, we move on to the shaft models, which gives us most of our output variables, such as the iterative coke method for method for calculating coke rate. And then once we have that data set, we can move on to the interpolation model. So the way the interpolation model works is we take two values for each input condition from the data set, and then we arrange every combination of the chosen input conditions into a matrix with known outputs. The matrix is then solved using linear algebra to find coefficients relating the input conditions to the outputs, and then the coefficients found from solving the matrix can be used to form an equation that can be used to predict values for input conditions not listed on the data sheet. So here is our flowchart for the interpolator software. It starts with a user loading a data set, and then the user can select a number of input conditions. And then once the input conditions are entered, we move on to the simulator pulling two nearest values from the data set. And then from those two values, the matrix is created, and then it's solved for within the program. And then the user selected inputs are plugged into the equation created from the solved matrix. From there, you can either choose a new data set to represent a different blast furnace, or start over with a different number of conditions, or just different conditions in general. This does mean with each input, a unique matrix is created for maximum accuracy and prediction. Here we have some sample CFD results from the TWEER modeling. This deals with a single variable, in this case, the natural gas temperature. And you can see that we do gain positive impacts from preheating. This results in higher gas temperatures in the Tweer and Raceway, about a 0.147 Kelvin boost in raft and a 1 Kelvin boost in natural gas temperatures. Heating the natural gas results in an increased velocity, which promotes better mixing and combustion. And on the shaft side of the CFD results, we have all 6 levels of the natural gas preheating, including gas species content, mass flow rate, temperature distribution mapped from the CFD Raceway simulation. So the Raceway is kind of an intermediate step between the shaft and the Tweer. And then the coke rate, you can see that the coke rate falls with increased natural gas temperature, reaching a decrease of almost 9 kilograms per ton of hot metal at the 300 K preheat level. This aligns with our rule of thumb that the top gas temperature declines with increased preheat, but it results in an increased Raceway flame temperature. So here we have an example of the interpolator software. At the bottom is an excerpt from our data set to compare our results. And then here the user can enter their desired input conditions. We're starting with the first line taken directly from the data set. And then you can see the results are nearly identical to what is on the data set to showcase the accuracy of the program. And then now we have a second set of variables also from the data set. Following that, we will feature 2 inputs not on the data set, one between the 2 values, and then one outside the parameters. And then again, this matches up pretty well with the data set. And then for these in-between values, you will see that it is somewhere between what you would expect these 2 data sets values to be. And again, it's what you'd expect. And then this last example will showcase the simulator working with data sets with inputs outside the data sets. And then this results in what seems to be reasonable values, and none of these are included on the data set. So in conclusion, we have a software that allows operators to access CFD data rapidly and interact with it. The program can be used effectively on any device ranging from PCs to smartphones due to its small size, and a program that provides a simple user interface to allow for iterative exploration of the process, as well as a useful training tool for operators and students. And due to its modular nature, it has potential to expand to a fuller digital twin. So for future work, we would like to include further simulations of the new blast furnace technologies. Our software does result in long-term use, as most of it is just kind of based on being able to input different data sets of your choosing to simulate different blast furnaces. We want to allow for user-defined variables and outputs, so you can choose exactly which variables you want to change and how many. And then we would also like to incorporate a numerical optimizer. We have a numerical optimizer, but it only exists in the command line version written in C++. This version was written in C# for better compatibility with the GUI. And then we'd also like to develop an interpolation model for the CFD generated contours shown in the Tweer modeling and the shaft modeling. And then special thanks to MathNet Numerics for the open source library used in the simulator code. So C# does not natively support linear algebra, which is what a lot of the interpolator method is based on. And then special thanks to David Johnson, another Civ student and senior design student responsible for CFD and post-processing. And then a thank you to the Steel Manufacturing Simulation and Visualization Consortium for providing the CFD models and baseline data sets. And then thanks to fellow Civ staff and students for providing resources to allow us to continue working on the project. Okay, any questions?
Okay, Nicholas, thank you very much. Our last presenter is João Cardoso, and he is from the Federal Center for Technology Education of Minas Gerais, Brazil, and his presentation is statistical analysis to determine the thermal effects on mechanical properties of a metallic alloy part.
Okay, can you see my screen?
Yes, we can, and we can hear you.
Okay, thank you, Kevin.
You're very welcome.
Okay, good morning, everyone. My name is João Migliorini. I'm from Brazil, state of Minas Gerais, and I study mechanical engineering at a university called Cefet-MG. That means Federal Technology Center of Minas Gerais. And today I'm going to present a series of experiments carried out by students in our university. And these experiments had the objective to investigate metallurgical effects in a metallic alloy part. So the name of the research is Statistical Analysis to Determine the Thermal Effects on Mechanical Properties of a Metallic Alloy Part. So this is the summary of the presentation. First, I will introduce you all the context about the project. Then I will present the problem and the methodology that we chose to solve it, the results, conclusion, and finally suggestions for future research. First of all, I need to introduce you to Formula CFAST. This is an extension program of my university for engineering students. Basically, it's a competition team composed only by students, and it has the main objective to design and manufacture a race car for engineering students competitions. This type of extension project allows the students to be closer to real engineering problems and allows for interesting integration of different areas of knowledge. For example, mechanical, electrical, computational, and metallurgical. And it also stimulates the teamwork and enables the participation in national and international student competitions. So the main challenge of the team, Formula CFAST, is to design a light, resistant, and fast car. And to do this, the designers have to think and plan all the steps of a part, such as choice of materials, choice of manufacturing methods, simulations, calculations, and optimization. And in this presentation, I will show you why the choice of materials is very important for the performance and reliability of the parts, and how the students use the principles of the metallurgy to investigate a material failure and present solutions for an engineering problem. So, the motivation of the research is to investigate the failure of the wheel hub, a part of the suspension system of the car. This component connects the wheel to the suspension. So, of course, it's a critical part and must be reliable. Since this is an important part, it requires a lot of simulations and calculations to guarantee the reliability during the season, the tests, and the competitions. So we carried out structural, fatigue, and dynamic simulations of both the separated part as well as the whole suspension system. But despite all the calculations, the front wheel hub broke during a test much earlier than we were expecting. And this fact motivated the team to investigate the failure. So to solve this question, first, it's important to emphasize the material that was chosen to manufacture the part. We chose a special aluminum alloy 7075 T6, which can achieve great values of tensile strength and yield strength, and of course has low density. The code T6 means that it's a heat-treated alloy with precipitation hardening. And this is very important because, as I said, we need to manufacture a light and resistant car. It's also important to understand this heat treatment, the precipitation hardening. And it has three main steps. First, the alloy is heated to around 500 degrees Celsius. And this temperature is kept to allow the formation of the solid solution alpha, as you can see in the phase diagram. Secondly, the material is quenched, normally in water, in order to freeze the supersaturated solution. And finally, the alloy is subjected to the artificial heat aging at around 120 degrees Celsius for some hours, which allows the formation of fine precipitates. And these precipitates block the movement of the dislocations, forming a high-strength alloy. So getting back to the problem, a hypothesis to explain what the possible cause was the thermal influence caused by the brake discs. I will explain. The brake discs are the components that use the friction in order to stop the car's movement. And this friction releases a lot of heat right next to the wheel hub. And with conduction, convection, and radiation, the heat is transferred to the wheel hub, affecting the heat treatment and causing a phenomenon called overaging. This phenomenon causes a decrease in strength because of the coalescence of the fine precipitates. As you can see in the graph, the yield strength decreases as the temperature and time increases. And the same behavior occurs on the tensile strength. So this was the hypothesis that motivated the team to study the thermal effects on mechanical properties of this special aluminum alloy. So to study the thermal effects, first, of course, we need to measure the temperature. So the team installed thermal sensors on the surface of the wheel hub during tests of the vehicle. Another important point is the time that the material, the alloy, is exposed to the high temperature. So we measured how long the car moves during the test day using the GPS of the car. And to evaluate the thermal effects, the team used the design of experiments technique to plan tensile tests. Initially, tests were carried out with the material at room temperature in order to determine its mechanical properties, such as yield limit, tensile strength, and elongation. And then we planned tensile tests considering three most important variables with their respective levels, according, of course, to the measurements. So these variables were the preheating temperature with levels of 100, 200, and 300 degrees Celsius to simulate previous runs to which the wheel hub might have been subjected. Similarly, the preheating time of 12, 24, and 36 minutes. And tensile test temperatures with 100, 200, and 300 degrees Celsius to simulate a possible failure during a run. So to carry out the tests, the tensile samples were machined according to the AISTM norm, and the machining operation was done at Cefet-MG, my university. And the tensile tests were carried out at the Mechanical Testing Laboratory of the Nuclear Technology Development Center, the CDTN, located in Belo Horizonte, Minas Gerais. Now I'm going to show you the results of the experiments. First, the curves representing the tensile tests at room temperature. And the responses of the tests of yield strength, tensile strength, and elongation. And as you can see, it's a very resistant aluminum alloy. Now, the curves obtained at the test temperature of 100 degrees Celsius. And at the top, you can see the conditions of preheating time and preheating temperature, as well as the respective responses. Now, the curves at a test temperature of 200 degrees Celsius with their respective conditions and responses. And finally, the curves obtained at the test temperature of 300 degrees Celsius. And as you can see, since the beginning, there is a huge progressive decrease in the mechanical properties, reaching more than 80% of reduction in the yield limit, comparing to the test at the room temperature. As I mentioned, we modeled the response of the variables with design of experiments, And this Pareto chart is the most important visualization that shows the influence of each variable on the yield limit, which is the most relevant property of our study case. As you can see, the test temperature is the most important variable, which explains more than 50% of the yield limit according to the model. The other graph shows the influence of the variables directly on the yield limit. And this visualization also allows us to conclude that the test temperature is really the main variable. These results show that the model is statistically significant, and we can see it through the R-squared and adjusted R-squared. These values are really close to 1. That means a good model. And as you can see in the normal probability plot, the most part of the residual is right close to the normal line. So, as conclusion, after the results, the team designed a new wheel hub with the same material, the same aluminum alloy 7075, but with a new geometry, as you can see. And this geometry allows the part to be further away from the friction area of the brake discs, facilitating the heat dissipation and helping to avoid the conduction between the wheel hub and the brake discs. Another important action established in order to achieve more reliability was the project of a cooling system for the brake discs that conducts some rain air to the part, reducing the temperature of the component. And the team also changed the organization structure, creating a material squad or material team with guys responsible to all the choice of materials of the car through deeper studies about mechanical properties and thermal influence. And finally, a picture of the team celebration, only to show that the students solved a complex engineering problem using the principles of the metallurgy. And it's also important to emphasize that the team won the 2018 Brazilian national competition, and this project certainly helped to achieve this wonderful result. So, as suggestions for future research, it would be great to increase the number of experiments and the other range of variables in order to guarantee a completed study of the thermal influence. In order to complete the mechanical properties analysis, it would be necessary to study the fatigue of the alloy and the thermal influence. And another important suggestion is to reproduce this type of study in other materials and test another type of materials to manufacture the wheel hub. So I would like to thank all of you, thank AIST for the opportunity, thank UFMG Student Chapter and its respective sponsors, thank Professor Ronaldo, Cefet MG, my university, CDTN, for, of course, Formula CFS team, and my colleague Vitor Santos that helped from the beginning to the end of this project. Thank you so much.
Thank you. Any questions? Okay. Well, first of all, this concludes the student paper competition. And I want to thank AIST for providing me this opportunity to once again be the moderator. I'd also want to thank all the students for their presentations. Excellent job again by all the students, so congratulations. I would remind everyone that the winners will be announced at the AISTech Steel to Students reception on Tuesday, the 29th of June, beginning at 6 p.m. at the Vanderbilt Room at the Westin Nashville Hotel. For those of you who can't attend the reception, the winners will be announced Tuesday evening at the AISTech daily email that is sent out to all of the AISTech 2021 registrants. And with that, I say thank you very much, and back to you, Courtney.
Thanks, Kevin, and thank you for serving as our moderator today. And also thank you, of course, to Kelly and Amy for serving as judges. And thank you again to the students, all of the students that participated today.